Swayam Prabha. Digital India. Educated India.
So yeah, to summarize, I think what we've gone through till now, I think, right, we saw what is the motivation. So the motivation is the fact that we have so much of data which needs to be processed, that the way the type of data has also changed from structured to unstructured, and so we have seen this huge explosion of data. You've seen that compute has not kept up, I think, with this level of data. I think the fact that Moore's law has kind of come down, and we went from single core CPUs to multi-core to be able to handle some of the challenges. But then that came up with its own challenges because multi-core could not scale beyond a point. It required parallelization of the application code itself, and beyond a point that is not possible. And then the other challenge which we saw with multi-core was that the number of cores kind of kept growing at a pace which could not be handled by other components like memory and IO on the fabric. And so these were challenges which had to be solved. And we also saw that some of the improvements in this space which has led to making things a bit better. I think we uh, looked at the fact that compute has become a lot of the SoC kind of architectures have become more prevalent. So been able to get memory closer to the CPU. We've also seen things like photonics and silicon photonics happening, which kind of mitigates the effect of this communication overheads which are there. And we are also seeing some of these things like persistent memory which has come, which can give rise to new paradigms of applications and things like that, as well as fabric protocols like Gen Z and CXL to handle some of the challenges which we are seeing with DDR and PCIe. So that's kind of where we are. I think we have seen this thing that things are getting a bit disaggregated. I think compute is kind of getting disaggregated from memory and IO in some sense, and that's where I think software architectures also have to start thinking. And as we so this next so yeah, this cartoon basically indicates where we are, right? I think it's a quote from Winnie the Pooh. You just have to probably stop and think whether there is another way of doing things, and I think that's where we are heading. I think software folks have also started thinking of what are the new ways of handling this kind of disaggregated architectures. So uh, so yeah, this is a slide which basically says that we are now defying the conventions of computing, and we are moving to this era of unconventional architectures, unconventional programming, and unconventional accelerators. I think these are the three things which are probably happening to kind of change the whole computing paradigm and the way we've been looking at things in traditionally. So if you see the traditional von Neumann computing, right? I think where we had the control unit, and the CPU was basically the control and the arithmetic unit, and then it was attached to the memory unit, and the instructions as well as the data were part of the same memory unit. I think that has kind of changed a bit now, right? I think we are seeing this persistent memory coming in. So you have the CPU separate, the arithmetic logic separate with some accelerators and things like that, and having its own persistent memory. So that kind of evolution is now happening. And then probably the next era of evolution will be where everything is kind of pretty close to each other and connected through an interconnect or something, or could be even separated from each other and separated by a fabric or something like that. And then there'll be something to do some configuration of this whole thing, right? I think how much CPU do you need, how much accelerator do you need, how much memory do you need, all this could be probably configured through some kind of logic. So that's where I think things are heading, and that's probably the evolution of von Neumann computing. And so one thing which I think we have tried to do in HP, I think, is try to look at this changing kind of landscape and seen what do we need to do from a software perspective, right? And even from a hardware and software perspective. And HP came out with this thing called memory-driven computing. So I think today's architecture, if you see, it's everything is constrained by the CPU, right? I think, like I talked about, and you cannot exceed what a CPU can handle uh, on the system. So what we are moving towards is something like a memory-driven computing model paradigm, where you can mix and match. I mean, basically at the speed of memory. So you can have memory which is outside the CPU. You could have multiple types of disaggregated CPUs like RISC-V or ARM or x86, and you could have accelerators in there with GPUs and FPGAs and things like that. And memory could be of types like DRAM, it could be PCM, it could be storage class memory, it could be flash. You could have some specialized devices like optical devices or neurocomputing devices. All this could, if they can be matched up now with a fabric, I think that's kind of the architecture which is being conceived and visualized. And this architecture, what we feel is probably can scale from edge to the enterprise and the cloud, right? I think you can have an edge device also where you can have this kind of uh, architecture, and you can have a cloud one also where you just need to now probably have composability. You need to have that configurability associated with CPU, memory, and IO, right? If you can decide how much you need to attach one to the other, and then you can do whatever you want. You could be an edge device, you could be a cloud, you could be a big memory machine, or you could be an exascale computer. So it kind of simplifies things from a software perspective, because the software just needs to be made. I mean, from an application perspective, it just needs to have the access it needs, whether it needs a large amount of memory or a large amount of accelerators or a large amount of IO. So you basically configure the system for that, and then you have the application run for that. So that's kind of the high level hardware architecture which the MDC talks about. And this is another slide which basically shows the same thing which I've been talking about. So it's called what is called a memory semantic fabric, right? So Gen Z, like I talked about, and even CXL, even though they are packet protocols, I think they enable the fact that you can have load stores. So you can actually, it's not like IO where you are actually just doing communication kind of asynchronously, right? Like what Adi was talking about. What CXL and Gen Z enable is the fact that we can have a memory semantic fabric. So you can have a load store at a higher level. That connected load or a store is enabled through a packet protocol, but it gives you that memory semantic fabric. So you can access the fabric as if you are accessing memory. So from a processor perspective, it will still continue to do a load store to a particular memory location, but then that will be handled by the Gen Z or the CXL fabric. And so you could have different processors like x86, ARM, RISC-V. You could have memory which is persistent, like I talked about, flash, GPU, FPGAs. Then there are some new accelerators coming up. So you like, I will talk more about the dot product engine, and then there's chaos computing, there's optical computing, there is the whole quantum computing space which is coming up, right? So all this I think is where uh, systems are kind of heading. And all these systems, like I said, can now be composed. I mean, it's not something where you're kind of fixed in terms of the way you are doing it with a single CPU system or something like that, right? Where you have everything kind of stranded within that particular system. Now you can have things which are outside. So it gives, so you can do a lot more things around resiliency and things like that. You can make sure that things are rated and things are made more reliable. Multiple folks have access to the same fabric, the same memory. You can do shared memory. So it gives rise to a whole new way of thinking of applications and how to solve the problems which applications are solving. So if we look at memory driven computing, right, it how, what does it basically do? So one thing which we looked at from HPE, I think, was with MDC was huge memory systems, right? I think kind of the scale up kind of scenarios, applications which required really huge amount of memory. And some of the examples of things are like similarity search, right? So similarity search is basically the idea that if you have a particular image and you have a whole database of images and you want to see which one this image matches to. So the fact that if you have a huge amount of memory, and at that memory scale, you can actually go and look through things rather than having to go to a disk or do something. It really improves the real-time latency of some of these kind of applications. Similarly, search space optimization, right? Things like airline reservations and things like that. For instance, I mean, if you have all these in memory, where you can actually think of all the routes which are there for a particular person to go from one place to another and do that whole programming of a person's trip or something like that. That kind of is solved by having this huge amount of memory. The third area which we looked at was financial modeling. I think in terms of things like the stock market and things like that. I think the Monte Carlo simulation which happens there. If you have this huge amount of memory, you can actually do a pre-compute and save a lot of the memory, a lot of the Monte Carlo kind of simulation data which is required in memory, and then you could just reuse it to do the computation when you need to. So it's a kind of paradigm where you can shift, where you can, the type of application, if it is benefited by that huge amount of memory and pre-compute kind of thing, then it serves that purpose. Similarly, you can now share memory with an MDC architecture, right? So if you have memory out there, you could have multiple nodes which are trying to share that same memory and doing compute on it. So you could have like Spark. We in fact modified Spark for that kind of scenario and could see the benefits of it. Similarly, there are other areas probably with neural net training where you could divide the networks among multiple nodes and do the processing because it's in shared memory. And the third part it enables is not the non-volatility of memory. I mean, if with persistent memory, the fact that it is memory with non-volatile, I think you can do a lot more things. You can probably now change the programming models. I think, and it has happened with Intel itself investing a lot of effort into PMEM and the lib PMEM work and things like that, right? I think you would have seen a lot of advances in that space in terms of actually programs be modified to be able to access non-volatile memory and have key value kind of programming and things like that in non-volatile memory. So that's another area where things have where software has changed. And finally, dynamic range, right? So dynamic range basically alludes to the fact that now you can do all this from an edge to a kind of cloud kind of scenario. So based on what is your requirement, you can compose the system accordingly, and then you can have your application run on it. So that's kind of what the MDC architecture enables. So that's the unconventional architecture which I talk about. And then there are what are known as unconventional accelerators. So this paper is from this graph is from the Hennessy and Patterson talk, and it's interesting that the number of machine learning papers they've shown that it's probably scaling at the same way as a Moore's law. So maybe it's the new Moore's law of machine learning, I guess, in a sense, right? I think so. Machine learning has become the big thing now. I think most of um, the work, if you are seeing nowadays, I think is going into machine learning, deep learning, and similar technologies. I think, and I think Suparna will also probably talk a little more about that because that's her area of specialization currently. At the end of it, we can have a discussion about that. But that's where things are heading. So machine learning, what it places requirements on the system, is where you see a lot of development happening in terms of computer architecture. And AI architectures are also evolving, right? I think from standard CPU based programming, which doesn't scale because it's a general purpose CPU, and AI and neural nets and things like that have like specialized requirements, like which are more similar to a data flow kind of thing, right? I think with matrix multiplications and things like that. And so we had this initial thing with GPUs. I think GPUs, as you know, you can parallelize a lot of things, right? You can just give multiple data and then do the same thing on it. And so the SIMD kind of processing was I think was probably the first step in AI architectures. But then that's now moved to things like systolic arrays and CNNs, where actually it's become more of a data flow architecture, where you can actually have these arrays of nodes, and then you have data which is flowing between each of these array nodes, and then computation is happening on them. We are also seeing that there's both big cores and little cores. I think based on the application, I think it depends on like what you're running. I think you can see benefits to both of these models. I think Cerebrus has, I think, maybe 40,000 cores or something like that. It's a single wafer on a chip or something like that. It's really huge, I think, right? And on the other end, you have something like Graph Core or Grok, which are like in the low single digits in terms of number of cores. So I think you have both these kind of models, and both of them are kind of working for their kind of problems. The other change, like I said, the architecture is changing from a multi-core architecture to a data flow kind of architecture. I mean, it's actually data which is flowing to the corresponding compute, and then the computation is happening on it. There's something called a terminology called CGRA, so coarse grain reconfigurable architecture, where things are now, I think the compiler, there's a compiler coming in which is actually deciding where to run a particular compute for a machine learning or a AI kind of application, and then the data flows to that particular node. And then you also need to make sure that the data accesses are fast. So what can you do to make the data accesses fast? Again, this is an area where HPE has done a lot of work. I think with DPE, I think in the next point which you see around analog computation. So we have mixed both of these models, the CGRA kind of compiler programmable model, and an analog computation. So instead of doing a digital computation, we've used our work done with memristors, and I'll talk a bit more about that, to be able to do an analog computation. And there are a lot of other companies who are doing the same thing. I mean, IBM, Ambient, Mythic, all these. Mythic is in fact probably the most popular of these in terms of doing analog computation in the deep learning space. And finally, there are even more esoteric stuff, right? Like photonic computation. So Light Intelligence is the company, I think, which has come out with something like where they can do these matrix multiplications in using optics. If you know lenses, I think they already do things like Fourier transforms and stuff like that. So if you can use light in some way to do matrix multiplications, I think that is ideal for deep learning kind of application. So there's a lot of work happening in that space too, and even HPE has been working on some of the photonics related neurocomputing kind of applications. I'll talk a bit more about that later. So that's again another area where things are evolving. So this is where I think just to give you a high level overview of how AI architectures are evolving. And so from your traditional architectures, which we were more aware of, like in terms of CPU, memory, and IO being close to each other, and then just programming like a von Neumann programming, we are now changing to this era of this data flow kind of programming, and being able to uh, kind of shard the data across multiple nodes and be able to compute as required. So just to give more insight into the dot product engine. So like I said, it's based on memristor. So and memristor was a what was kind of, it was called a fourth property kind of thing, right? I mean, like you have resistance and voltage, current, and resistance, and then some. I mean, something like that. I think it was a new property in terms of like a conductance kind of thing. So if you see a current which is flowing out from the circuit, if you have a crossbar kind of circuit of all these memristor entities, then you can see if you supply voltages on one side to each of them, you can get through this memristive element, you can get current on the other side with this formula, which is using G as the conductance, I think, in this case. And so you can see that in an analog domain, you're able to do actually a matrix multiplication. So if you have a vector of voltages, which is input on this left hand side, and if you have this crossbar of matrix, it's like a matrix of uh, memristor entities, then you can actually do an analog computation and get a sigma of Gij Pi, right? Which is a basically a matrix multiplication which you're able to do by just these elements in analog domain. So that's very interesting, because now the huge challenge with matrix multiplication and these deep learning applications is that you have to do this computations on compute CPUs, and that takes a lot of time, because you have to go through each of these in an iterative manner. For instance, on a CPU, if you have to do a matrix multiplication, you can imagine, I mean, how many steps you have to go through. And though this has been optimized with GPUs, it still requires multiple steps. But in an analog domain, if you have a crossbar like this, and the Gij's could actually correspond to weights, which you see in a neural network, right? For instance, the matrix which corresponds to the weights. So you give an input vector and you can get an output vector in almost instantaneous time, and that's a very huge improvement over doing it computing in the digital domain. But then the challenge which we have is that data is digital. I mean, so we have to be able to convert it to this analog format of a voltage and be able to do this computation, and then again convert back to digital. So those are challenges which we have from a hardware perspective to be able to realize this. But those are being worked on in terms of how to reduce that overhead of conversion from digital to analog and analog to digital. The other challenge, I think, which is very common in machine learning today is quantization. I mean, when you have this data, right, how important is it to maintain the full fidelity of that data, or can you actually quantize it? Can you make it a bit more coarse and still be able to get what you want? Because machine learning is more of an iterative thing, right? So a lot of times you don't really need that level of accurate input, accurate weights or something like that. You could be able to learn it over a period of time, and you might not get as much errors in the final computation because of quantization of some of the data coming in. So that's another area where a lot of work is happening, even in the industry, I think, and it kind of helps this analog to digital and digital to analog conversions, which we've been looking at. So this is something which came up in the HPE labs, and in fact, I was fortunate to be involved in the compiler side of it from the India team side, and we did a lot of the work for the compiler side of it to be able to take a neural network or a convolution operation and be able to program it on some of these dot product engine crossbar nodes. The other thing which is very nice about this architecture is, like I showed you, it's a crossbar of memristive entities, right? And memristor itself has the property that it can actually store memory, and so you could actually have these weights stored on these crossbar entities. It's not something which you have to really keep reloading from somewhere or something like that. So it's a very interesting concept that you can actually use the crossbars both as memory and as well as you can do the computation also inline. So it's a huge benefit. So this is an interesting technology. I think Mythic does kind of similar things. So even though they don't use memristors, I think they use some other way of doing it. But it's an area which is getting a lot of traction, and I think you'll see a lot of this analog computing also growing there. So just to talk a bit more about it, I think you can go to this paper. So we actually worked with some students from university. I think it was University of Illinois Urbana-Champaign. There's a person called Ankit, and I forgot the other person's name. So there were two folks from that university, students whom we worked with, and we came up with this Puma architecture where you could have these tiles, and each tile basically corresponds to this crossbar chip which I showed in the previous slide, right? So you could actually have a compiler which takes a whole network and then a matrix, a whole neural network computation like a CNN or something, and then programs it on each of these tiles, and these tiles can communicate to each other through an on-chip network. So you can actually communicate some of the um, mid-level computation which is done, and then bring it all together in some final output tile, for instance, and then output it out. So there's a lot of interesting work, and you should, if you are interested in this area, just read that paper. I think you will find that I think it's very well written. It was presented at ASPLOS in 2019. And yeah, like I said, application layer could be a CNN, LSTM. We in fact showed it working with initially with an LSTM and then later with a CNN also. And the compiler is what we worked on, where we could actually convert to the assembly level code which runs on these tiles, and we had to map the weights to the crossbars and things like that. So it was very interesting kind of work. Also, I think we developed, along with the Brazil HP Labs team, we developed a simulator which could provide some of the performance metrics and things like that. So very exciting, interesting work, and where kind of you see architectures heading. I won't go much about this through the slide, but I think it basically shows the flow of how things flow. You have to build a task graph basically of the problem, map it to the crossbars, and then the tiles can do other computation also. So they're basically, you can have RISC-V processes in them. So you could do map non-dot product kind of, or non-matrix kind of computation also to the tiles. And then on the compiler would actually map, will do actually a, when the compiler creates the intermediate representation, it would be all virtual tiles. And then you could actually map these virtual tiles to the physical tiles which are present on in the actual hardware, and do it in runtime. So very, very interesting kind of paradigm. And then so this is just kind of the starting, I think, right? So like I said, there are more such unconventional accelerators being designed. I think there are the analog neuromorphic computing, this basically is the DPE stuff which I talked about, and then the optical computing, which is like the light intelligence stuff. I think there are other interesting problems being solved by this, which are also being solved by quantum computing. And so at one point, I think HPE was more into this kind of optical computing than quantum computing. We are not against quantum computing. I think we've not probably been put our weight fully behind it. It's probably, I think Suparna may be able to talk more about what's happening in that space. But I think it solves the same kind of problems, right? The NP hard problems which quantum computing could solve, like the traveling salesman problem. I think you could solve similar things with an optical computing. And we had actually a chip. So you can see below, if you see the chip, I think it's compared to a pencil tip, right, to show how small an optical computing chip could be. And so you could have multiple of these chips to be able to do the computation. So it's very interesting kind of hardware focused areas. And I think finally, I think I would like to end with unconventional programming. So it's not really unconventional. And we'll talk more about some other unconventional programming, I think, which is happening, I think, with Suparna. But I think this gives you an idea of where things are heading. So I think we've talked about each of these things in these 2 weeks, right? We've talked about bare metal, we've talked about VMs, we've talked about containers. So now we are getting to the we have already got to the serverless era, actually. I mean, if you see, I think, and Adi was asking this question about serverless versus uh, microservices, right? So I think microservices is another way of looking at it, is that microservices is more of the way of how you implement it, and serverless is probably the how you kind of the infrastructure implements it. I think if you can think of it that way. So it's like more of the software to hardware kind of abstraction of it. And in the serverless paradigm, what you can actually do is you can do function level computing, right? So you can have a particular function. So like in a cloud, what you do typically is that you take a, maybe you get access to a particular set of resources, and then you run your application on it. But with a serverless kind of model, you will just run a particular function on some set of resources, and you will not know where it's running or what it's running, but you will get a function and an output kind of thing. So that is the level of abstraction which it can go to, and you'll be kind of paying for only that uh, ability to run that particular function.
Huh?
Okay, so can you please go on mute? Yeah, can you hear me, right? Hello?
Yeah, you can be.
Yeah, okay.
Yes.
Okay. So serverless is where I think we are already heading. I think AWS and other cloud vendors like Google and others are already talking of this paradigm. And then where HPE sees all this is heading is what we call cloudless, right? I think in the sense that right now, even serverless, you would actually go to a particular vendor, probably like an AWS, and do something. But imagine if you could do everything kind of a global service mesh kind of thing, where you could run something on a particular cloud. You could have a hybrid cloud. You go to another cloud vendor and do something. But then that would require a lot of trust boundaries to be crossed and things like that. So that's where we feel things may change in terms of programming and how things will happen. And like I said, you'll require a trust fabric to be able to run a cloudless kind of computing. You'll need a connectivity fabric between each of these clouds, and you'll need different value fabric, right? You'll need different kind of partnerships, communities, within these cloud vendors to be able to achieve something like that. So that's kind of a vision that we've thrown out there to say that this is where we could have as the next generation of server after serverless computing. I think that kind of finishes my slide. As always, I end with Calvin and Hobbes, and I hope, yeah, with all the binding and all what I've said will look like a graduate thesis. So that's the end of my presentation. Is there any questions which are there? I don't know whether I had another slide. I thought I had one more slide. I think I missed it.
Yeah, hi. This
Yeah,
is, it's really great. I mean, a really great presentation, first of all. Thank you.
thank you.
I have a lot of questions, but it will probably take forever. So maybe I think
We
Suparna
can,
should
we
go
can.
first and then we
We,
can have a discussion.
okay, no problem. So yeah, so I think I had one more
Yeah,
slide.
feel free to ask questions. I mean, the purpose of the
Yeah,
discussion is also
correct.
really
So
to.
I had one more slide which where I wanted to talk about some of the things happening in HPE, but I think I forgot the slide. I don't know how that happened. I thought I'd put it in here, but anyway. So I think we wanted to kind of seed that discussion with things happening like MDC and then DP. I've already talked about two of the things. I think there are other interesting things happening called like swarm learning. I think I don't know if you've heard of it. Maybe you can Google for it. There's an interesting paper which has come out in Nature recently, where HPE has presented this idea around swarm learning, and you would have heard of fleet learning with things like Tesla and others, right? I think where you can actually do a learning over a distributed kind of set of nodes. Uh, Swarm learning kind of takes it to the next level with a blockchain approach where you can actually have security built into the whole thing, and you don't really need to share data between these nodes, and then you can actually have a blockchain kind of approach to be able to uh, do the learning framework. So there's a library also which has been open sourced, I think, and or available for license. I'm not very sure, but yeah, I think that's another interesting area where a lot of good work has happened. And then, like I said, I think Suparna probably has other things which she would like to talk about from a lab's perspective and AI and other things which she's been working on. So, but I think we can, if there are questions, we can take them. After that, we can probably stop this recording and then we can get into more open kind of discussions, I think.
Sure. So I'll ask I'll ask one question for now, which I think is more
Yeah,
relevant.
sure.
So I mean, these systems are now. Would you say they're scaling out, or would you say they're scaling up? I would say it's neither, right? It's neither scaling out nor it's scaling up.
It's
So
actually a neither. I think we had I think as part of MDC we had an interesting slide where we showed scale up versus scale out. I don't think I included it in the deck, but it is changing. I mean, it could be scale up where required. I mean, you could have a large number of amount of compute on the same fabric, and you could attach a large amount of memory to it and do a scale up kind of computing. You could do a scale out if you require. I mean, you could have a small compute device set of compute cores, and then you could have a large number of those accessing the same memory through a shared memory kind of thing. So I think you could do
Yeah, it's the same. It's a
both.
flexible architecture where you
Yeah,
can do both. Yeah, yeah.
yeah,
The ones which are closer are like scale up. The ones
yeah,
which are further out are like scale out.
exactly, yeah,
yeah,
that's a great term, flexible, right? So my question is exactly on this term, flexible. Now,
yeah.
when we think of something as flexible, we assume that it bends on its own and it comes back on its own, right? That is the meaning of flexible. The rubber comes back on its own. In the case of these systems, how much do you think the management or the automation of the control of these systems needs to be flexible? Do you think that that is a more interesting challenge, or the programmability, the programming of these systems is a more interesting challenge? Like, how much flexibility do you want to actually make them come to life? Because without flexibility, it's not going to happen.
Yeah, I think both are interesting challenges. I mean, as I see it, I think the first part of it is the one I think we are tackling right now. I think the composability part, right? I think which I talked about, where if you can actually compose these systems based on the requirements of CPU, memory, I/O, I think that's a very interesting challenge. And to make it flexible enough, like you said, right? I think based on the demands, if you can grow it or flex it down and things like that. So those are challenges which we'll have to address. We'll have to do that in a kind of real time kind of thing, to be able to really meet the application objectives, for instance. So those are going to be huge challenges which are there, and it will be interesting challenges to solve. But the other part around the actual usage of these fabrics once they are there, like I talked about, right? I think we've already made changes with Spark, for instance, in memory Spark, and like being able to do a shared memory kind of Spark. And so there are multiple of these software out there which we can change to this new paradigm, and we can exploit this new paradigm. I think, and there's a lot of interesting work happening in that time frame, in that area. Even in HPE, I think we are working with some defense institutions also in the US, for instance, on some of the things around memory driven computing and what are the applications which would benefit from it. So there's a lot of work happening in both the areas. I think
And it's
and
like
both
an
needs to
order of
happen.
magnitude
Yeah.
more difficult problem from,
Yeah.
when I was giving the Linux example of, of having to deal with many of these situations. This is like an order of magnitude harder thing to achieve that flexibility, I think.
Yeah, definitely. I agree with you guys. I mean, I see that flexible. I mean, so when people think of flexibility, they think, okay, I'm going to put my program on Amazon, and Amazon is magically going to give me infinite scaling, how they like to market their product. But I don't want to put my stuff on Amazon. I want it at my edge. I want it at my client level. And that is where flexibility goes for a toss. Then you come to this question of, okay, do I need an embedded system programmer or do I need a CPU? Like, what am I even trying to do here, right? So that flexibility is, people say these heterogeneous systems are coming, but until and unless we address, and I think kernel is probably one great place where we can truly address these challenges, because yeah, Linux is definitely here to stay. Everything apart, the hardware will change, the users will change, but the kernel, yeah, that's forever.
You never know. Right? Yeah. As much
Yeah, I don't know, but
as we love it, working on that, but yeah. Yeah, but I see your point. I mean, the thing is that because everybody is depending on that, right? So there is a lot of things that are built around that. So it's very,
Yeah.
that's kind of why it became one, that OS, one single OS kind of took off so much,
Yeah, but even
because
the
then you have,
OS space, there have been efforts to try and change that whole thinking around that, right? I think things like microkernels and all that. Even the university, even now the universities, I think, spend a lot of effort on that space, and so maybe we will see changes in that also. I think in the future, I think there were things like what is it called, Mesos or something, right? In between, I think, right, where we had some of those. Operating system kind of thoughts around a distributed OS, and so there are a lot of interesting things happening in that area also. So it's not that Linux is forever. I think there may be things which will happen to change that.
great. So let's, I don't know, I guess I really want to hear what Subodh has to say, or we can continue this open stage discussion forever.